Good evening, everyone. I welcome you all in a Sapience education. So today I am going to cover this type of topic. First of all, Carnot Engine, Carnot Theorem, and Carnot Efficiency. So all these three topics should be covered in this video. See here, what is Carnot Engine? It is a theoretical reversible heat engine operating between two temperatures. So it's a theoretical one, it is not a practical one. Okay, so it is operating this type of engine operating between two type of temperature, that is high temperature as well as low temperature. And this is the Carnot engine, and the engine looks like this, and this is the cycle. This is the Carnot cycle. Figure beside this is shows you the Carnot cycle. Here it is a pressure and volume diagram is there. So it consists of A to B, B to C, C to D, and D to A. So there are four processes will go on the PV diagram. So I will discuss each and every process in a details. Before that, we need to understand what is sign convention for work and heat. So whatever heat will be come inside any type of system, let us consider this is a system. So in this system, heat will come in and work will go out. So let us consider if heat is come inside the system, so you can take it as a positive. And if work is work is done by the system, then you can take the work as a positive. At the same time, if heat is being rejected by the system, so you have to take it as a negative. And if work is input to the system, work is done on the system, then we need to take work done on the system. So let us try to understand what is work done on the system. So let us consider this is a piston cylinder. Okay, and if work is being or pressure is being applied, it means that the work done is on the system. So in this way we can take is as a negative work. But what happens sometimes, there is a piston cylinder process and there's a gas, and due to heat energy what happens, it expand. So gas is applying a pressure, so work will be out. So this type of work is known as positive work done. I hope you have understood now. So there are four steps. So we will discuss each and every process here. Four process are there. So let us see here. First process is A to B, and A to B, it is a isothermal expansion. Why it is isothermal expansion? Because the temperature will remain constant from A to B, but what will happen? The volume will change. That's why it is known as expansion process. Now in this what happened, temperature will remain constant, but heat will be greater than 0, and there will be a positive work because there will be a work done by the system. At the same time, B to C, there is a point B and this is a point C. So B to C, so B is the adiabatic expansion. Adiabatic means what? The system having net heat is 0. So there is no exchange of heat, that is del Q is equal to 0. And in this way it follows P V to the power gamma is equal to constant. All this thing has been already taught in a previous video. If you want, then you can go and check out that video. Okay, so work done will be positive. From B to C there will be work done which will be positive, and from C to D it will be isothermal compression. So work done on the system, so say C work done is negative. Heat is rejected by the system, so that's why heat is known as negative. At this point, see here, heat is going inside, so heat is taken as positive. Work is done by the system because system is pushing the piston, so it is known as positive. Now from D to A, it is an adiabatic compression. So when it comes from D to A, so it is being adiabatically compressed. Adiabatically compressed, okay? Now the Carnot cycle consists of Carnot cycle consists of four processes. First of all, isothermal expansion process. So this is the isothermal expansion process from process from 1 to 2. So in this, what happened? Temperature will remain constant. If temperature is remain constant, it means that T1, see here, temperature T1 as well as this T1 both are same. Okay, but what is changing? Pressure P1 is changing, P2, volume is changing from V1 to V2. Okay, exactly what happens in a piston cylinder. What happens? See here. So this is the diagram of the piston cylinder. Let us see here. This is the piston and this is the cylinder, and there is a gas. So when we apply a heat on this gas, so what will happen? Gas will try to expand it. But what will happen? Temperature will remain constant, but gas will try to push this piston. So as soon as push this piston, so what will happen? Pressure will also increase as well as volume will also increase. So that's why pressure and volume is changing from process 1 to 2. Now we will talk about process B. B, that is your adiabatic expansion process. Adiabatic means, again I am telling you, adiabatic means Q, change in heat, or there is no heat exchange. So if there is no heat exchange, and but what will happen? Temperature will change from T1 to T2. Okay, so in this adiabatic expansion process, expansion means what happens? It expand the gases. So when it expand the gases, so work is done here. Okay, so work is done by this expansion. Got it? But one thing you need to understand, that here temperature is changing. One thing you need to understand, again I am telling you, here temperature is changing. So in this process 1 to 2, the temperature was T1, but as soon as it come from T1 2 to 3, the point 2 to 3, so the temperature become T2. After that, there is an isothermal compression cycle. So till this point we can understand here, till this point gas expanded. After that, gas unable to expand. So what happened? External force, external work has been done to compress this, so that gas will come out from this cylinder. So this is known as isothermal compression. So here temperature will see here, temperature will remain constant. Earlier its temperature was T2. After that also, from process 3 to 4, the process from process 3 to 4, the temperature will remain same. And this is known as compression process. So work will be done on the system. Okay. Now next is your fourth is your adiabatic compression. Okay. So adiabatic compression means, again no exchange of heat is happening. See, fourth process there is no exchange of heat. Fourth process, no exchange of heat has been there. See, in this system no heat is going outside, but only there is a Q in and Q out is in this process A and B. But at this last process there is no exchange of a heat. That's why it is known as adiabatic compression. So I hope you have understood all the four process. So first one process 1 to 2 isothermal expansion, 2 to 3 adiabatic expansion, 3 to 4 isothermal compression of the gas, and 4 to 1 again adiabatic compression. So this completes this four process complete whole cycle. That is, it goes from 1 to 2, 1 to 2, 2 to 3, 3 to 4. So all this process has been completed. I hope you have understood now. Now let us go more details about this process here. Since I will only talk about this process 1 to 2. So what is actually happen in this 1 to 2? Heat is given inside, okay, from 1 to 2, but temperature will remain constant, that is T1 and T1. So if temperature will remain constant, so heat will be absorbed by the system Q1 and work is also done by the system. So state will come from P1 T1 to final state, that is equal to final state, that is equal to P2, V2 and T1. Why again T1? Because temperature is remain constant. As we have already derived for isothermal process, work done is equal to mu r T ln V final minus B initial. Okay, so here final volume is V2 and initial volume is V1. So what happened? Work done from 1 to 2 is equal to Q1, that is equal to mu r T1 ln mu r T1, because temperature will remain constant and our range of a temperature is T1. It is into multiplied by ln V2 by V1. Why V2 by V1? Because V2 is the final and V1 is the initial one. So as per the previous formula, we have already discussed this formula. So if you want the work done, how to find work done, so you can just watch the previous video. I think it's a third part. So there you will able to understand why I am writing this work done from 1 to 2 as mu RT1 ln V2 by V1. I hope you have understood now. So already we have talked about the process 1 to 2. Now I will talk about process 2 to 3. So let us talk about process 2 to 3. So 2 to 3, what is happening here? So 2 to 3, what happened? Just now you have seen at this process 2 to 3. See what is happening? This is the process 2 to 3. This is process from 1 to 2. So it's getting expansion. So this is also expansion, but no heat is supplied. So it is adiabatic expansion process. So here from process 2 to 3, see, so temperature will change. That is T1 and T2. And since it is an adiabatic process, so adiabatic process has a formula. Adiabatic process has a formula P V to the power gamma is equal to constant. So here gamma will be used, where gamma is the adiabatic index. Gamma is the adiabatic index. Okay. So here you have seen that temperature is being changed from T1 to T2. And pressure, volume, as well as all this thing has been changed. So as we know that work done for the adiabatic expansion process, as we have already discussed, work done is equal to mu r temperature final initial work done from T is equal to T1 minus T2 divided by gamma minus 1. So if you want to derive this equation, so you can go to the previous video. So it's an easier one, how to derive the work done in an adiabatic system. So if there is a two temperature, final temperature and initial temperatures are there. So there are so many other relation also. So you will able to understand in that video only. Okay. So I hope you have understood what is the work done from process 2 to 3. Okay. But no heat is there. So Q2 to 3 is 0. But at this time Q1 1 to 2 or work done is equal to mu r T1 ln V2 by V1. So I hope you have understood process 2 to 3. Now let us talk about the process 3 to 4. So what actually happens 3 to 4? So see here 3 to 4, it is just a compression process. But what will happen? Temperature will remain constant. So that's why initial temperature was T2 and final temperature was T2. So work done in, there will be work done inside this. So work done is equal to also Q rejected. Heat is being rejected in this process. Heat is being rejected in this process, and this will be equal to mu r T2 ln V3 by V4. That is equal to initial volume minus divided by final volume. So I hope you have understood now. Now let us think about process 4 to 1. So this is a process 4 to 1 where it is a adiabatic expression, that is change in heat is equal to 0. Change in heat is equal to 0. Delta Q is equal to 0. So work done from 4 to 1 will be equal to what? Same mu r T1 minus T2 divided by gamma minus 1. Okay. So how many equation we have got? So we have got equation 1. This is equation 1. This is equation 2. This is equation 3. and this is equation 4. So this 4 equation we have got. Now the total work done. Total work done will be equal to work done from 1 to 2, work done from 2 to 3, work done from 3 to 4, and work done from 4 to 1. So here work done from 1 to 2 is your mu r T1 ln V2 by V1 plus mu r T1 minus T2 by gamma minus 1 for work done from 2 to 3, and work done from 3 to 4 is your mu r T2 ln V3 minus by V4, and this is equal to work done for a 4 to 1, it's a mu r T1 minus T2 by gamma minus 1. So this one got cancelled out. So finally total work will get is equal to mu r T1 ln V2 by V1 plus mu r T2 ln V3 by V4. Okay. So here we can understand the total work done is equal to mu r T1 ln V2 by V1 plus mu r T2 ln V3 by V4. So this is the total work done. Now efficiency. Efficiency, we know that everywhere we will talk about the efficiency. Whenever we want efficiency, efficiency means what? Output by input. Whenever we want efficiency, so this will be equal to output by input. So how much we are supplying a heat and how much we are getting a net work, so that is the output, the ratio of work done by amount of energy we have spent. So let us consider in whole cycle of the Carnot engine. So what is actually happen? Qs is the heat supplied to the system and Qr is the heat rejected by the system. See here, Qs is the heat supplied and Qr is the heat rejected. So from here you can understand. Again you just see, Qs is the heat supplied to the system, Qr is the heat rejected by the system. Okay, so see here, from high temperature to low to a heat engine, Qs is heat supplied, and from this engine to Qr as a heat rejected to the system. So the net amount of work done by the system will be equal to W. So how you will find a W? So as we know that this equation, that W Qs is equal to W plus Qr, just we have discussed in previous slides. So that is Qs, that is heat supplied minus heat rejected. This is equal to work done, right? This is equal to work done. Okay. Now here, see here, if you want efficiency, efficiency means what? How much energy we are supplying to the whole process. So there are how many process? There are 4 process. That is 1 to 2, 2 to 3, 3 to 4. So these are the 4 cyclic process. So in whole cyclic process, we are giving energy, amount of energy, that is equal to Qs. And how much we are getting? Work output. This is the work output. So if we got heat supplied, if we got the output, so we can easily find the efficiency. So I hope we can easily find the efficiency. So how we will find efficiency? So efficiency is equal to energy output divided by energy input. So what is the energy output? So actually our target is to get the work output. So we can write here work output and how much energy we are giving into the cycle. So only Q supplied. So now we have already declared that work output is equal to Qs minus Qr. So here we can put here Qs minus Qr divided by work input, that is Q supplied, and finally we can write here 1 minus Qr by Qs. Now we need to put what is the value of Qr and Q supplied. So from previous slides only, see here, that is the Q1 is the Q supplied, 1 to 2, that is Q supplied, and this is equal to mu r T1 ln V2 by V1, and similarly Q rejected is equal to mu r T2 ln V3 by V4. So this is the heat rejected. Okay, see here, heat rejected is equal to this one. So we have got the values of heat rejected and heat supplied. So can we put here? So when we put here mu r T1, see here mu r T2, sorry, divided by mu r T1, ln V3 by V4 divided by ln V2 by V1. So finally mu r got cancelled out. So finally we are getting T2 by T1, and this is equal to ln log V3 by V4 by V2 by V1. Now it is a time to cancel this both one. So how you will cancel? Only if there is a V3 by V4, this will be equal to V2 by V1, then only we will be able to cancel it out. Now let us see what to do now. As we know that there is an adiabatic process. As we know that there is an adiabatic system. So in adiabatic system, P V to the power gamma will be remain constant. So since PV to the power gamma will remain constant, so in place and also one of the equation, general equation, that is PV is equal to mRT, we know that. So can we write in place of P, we can write here mRT by V. See, P is equal to mRT by V. So here I have put here P is equal to mRT by V into V to the power gamma, that is equal to constant. So finally this is your T into V to the power gamma minus 1. Why? Because there is a lower part is a V, and rest of the part will be remain constant for the same particular mass. Now as for the process from T to 2 to 3, 2 to 3, it's a adiabatic process. So here 2 to 3, can we write here, since T1 V to the power gamma minus 1 is equal to constant, so can we write here T1 V to the power gamma minus 1 is equal to T2 V to the power V3 to the power gamma minus 1. Just we are talking about 2 and third process. So for second process V to the power gamma minus 1, third process V3 to the power gamma minus 1, and this will be T1 and this will be T2. So finally V2 by V3 is equal to T2 by T1 into 1 by divided by gamma. See here how I have done here. So first of all I can break here steps. So you just focus on this. So how you will break the step? See here, this is a V2 by V3 to the power gamma minus 1. This is equal to T2 by T1. So finally V2 by V3, this is equal to T2 by T1 divided by 1 by divided by gamma minus 1. So when I break this statement, so you have got V2 by V3 is equal to T2 by T1 1 by gamma minus 1. So this is the equation 1. Okay, now let us consider same adiabatic process but in a compression one. So that is a fourth one, that is adiabatic process. So T V to the power gamma is equal to constant, we have already shown here. So can we write here T2 V to the power 4 to the power gamma minus 1 is equal to T1 V1 to the power V1 to the power gamma minus 1. So can we rearrange this? T2 by T1 is equal to V1 by V4 to the power gamma minus 1. So if we rearrange it, so finally we are getting T2 to the by T1 to the power 1 divided by gamma minus 1. This is equal to V1 by V4. So finally this is the equation V2 by V3 and V1 by V4 both have a T2, both have a other equation T2 by T1 to the power 1 by gamma minus 1. Both are equal to T2 by T1 to the power 1 by gamma minus 1. It means that this part as well as this part both should be equal because both have a same common equation. So finally we will get V2 by V3 is equal to V1 by V4. So can we rearrange this? So V2 by V1 can be written as V3 by V4. So this equation can be now shift to Carnot efficiency. So earlier we have got that 1 minus T2 by T1 into ln V3 by V4 divided by ln V2 by V1. Now what happens? We know that V2 by V1 is equal to V3 by V4. So here we can put in place of V2 by V1 we can put here V3 by V4. So we can cut this. So when we cut this, so finally our equation for efficiency will be equal to 1 minus T2 by T1, and that is known as Carnot efficiency. I hope you have understood now. So this is the final. So you can also write Carnot efficiency as 1 minus T lower temperature divided by high temperature only. Okay, always lower temperature should be at the top one and higher temperature should be at the bottom one, so that you will able to find the efficiency of the Carnot cycle.